I know Ali Jaballah gave a talk. He's a colleague. I missed that. And Muhammad Ashraf and many others. They gave I'm very sure they gave very interesting talks. Okay, I supposed to talk about the graph, but then I will be honest with you. This month, I had like 5 invitation in India. And in fact, I was not sure if I will attend this one or not. And the other 4 are on a graph. So I mixed up. I thought this one also on a graph. It turns out this one is a little bit different. It's about rings and, commutative rings. And so I decided to change the title of my talk.
It's
In
okay,
the,
sir.
and it's okay because, all my talk on a graph, you know them. So I think maybe this is somehow more recent talk. Okay. So I'm going to speak on one absorbing primary ideal. This is a paper that appeared in Journal of Algebra and its application in 2019 or 20. And I think, this concept of absorbing become more popular. There are many algebraists in commutative rings. They generalize this concept. Okay, so let me start with the definition and introduction. So throughout this talk, can you see my slides? Okay,
Yes, sir. Okay.
okay, thank you. All rings are commutative with identity. And if the ring has exactly one maximal ideal, then we call it a quasi-local ring. I know many authors, they call it local, but I'm using the school of Gilmer and Kaplansky, and they use quasi-local. So if you have a proper ideal, we call it one absorbing primary if whenever non-unit element A, B, C in R, so here is you have to pay attention about A, B, C. They are non-unit elements. And A, B, C in I, then I want A, B in I or C in the radical of I. That's the definition of one absorbing primary ideal. Uh, Being in this area, I always consider the first slide is the most important one. You want to know what I want to talk about. So if you want to follow my talk, you need to know what I mean with one absorbing primary, definitely. And remember that my elements, A, B, C, are non-unit element. Okay? Recently, this concept, they generalized this concept recently to one absorbing prime. They remove a primary and they study one absorbing prime. And what absorbing prime means is still the same thing whenever you have ABC in non-unit again and ABC in I, then AB in I or C in I. You see the difference? In the one absorbing primary, I want AB in I or C in the radical of I, where one absorbing prime means AB in I or C in I. And this concept also been studied recently by at least I saw 3, 4 papers on that concept. Okay, so here is the picture. A primary ideal definitely will imply one absorbing primary, and it will imply two absorbing primary. Okay? Uh, you can pick up the definition of two absorbing primary. This concept been defined long time ago. So let's study some properties of one absorbing primary ideal. Then, this is what I told you, nothing. If I is a primary, we recall what the primary mean. Whenever you have x, y, and I, then x and I or y and the radical of I. Of course, x and y, you choose them from the ring R. Okay? By the way, two absorbing primary, since I mentioned it again, I will tell you the definition. Two absorbing primary ideal, it means this. Whenever you have A, B, C, and I, then AB and I, or BC in the radical of I, or AC in the radical of I. Okay, and ABC here selected from R. Remember in the definition of a primary, one absorbing primary, I select my three element to be non-unit. Okay, here is an example. You take A to be a field with two variables, and you take this maximal ideal and you do the localization. Then R become quasi-local. We know that. You localize at a maximal ideal, and you take this ideal X. You take the maximal ideal of R and you multiply it with X. So you come up with that. This ideal is one absorbing, however, x, y, and I, but neither x in I nor y in the radical of I. So what we conclude, this is an example of one absorbing a primary that is not a primary. Because if it turns out that the new definition will give you primary ideal, then why bother? So as you see, I started the paper with this example to show you that one absorbing a primary does not imply a primary. But maybe it will, I mean, when I proved that, I was so surprised. I could not believe it that for if the ring is not quasi-local, then primary and one absorbing primary, they are the same. And that surprised me. Anyway, so first thing, look, if you want to follow my talk, here is my ring R quasi-local. I constructed an ideal. This ideal here, I took the maximal ideal in R and I multiply it with X. And this ideal is absorbing primary that is not a primary. Okay, here is an example of two absorbing a primary that is not one absorbing a primary. Remember what two absorbing primary mean. You select your element ABC from the ring R. And when ABC in R, you want AB, when you select ABC from R, and you have ABC in I, we want AB in I or AC in I in the radical of I or BC in the radical of I. Let's look at this example. It's all like, real life example. Take your ring to be Z, the set of integers, and you take the ideal 12R. Then I is two absorbing primary ideal. You can check that. It is two absorbing primary ideal because of the factorization of 12 in a way. Whenever you have a product of a three element in here, then a product of two should be here, or AC has to be in the radical, or BC has to be in the radical. And all of us know what's the radical of this is 6i, right? You can check that. However, here is a product of three elements. They are non-unit, but 2 times 2 is 4, which is not in I, and 3 is not in the radical of I. So I is not one absorbing primary. Okay? If I is one absorbing primary, then the radical of I has to be prime ideal. And this is like the same thing as for a primary. We know this result is true for a primary, that if I is is a primary, then the radical of I will be a prime ideal. Okay, very good. Uh, uh, okay, let me stop for a minute here. What about if I is too absorbing a primary? Then the radical of I think we proved that the radical of I will be too absorbing ideal. If I'm still, my memory did not, you know, deceive me. Okay, here is the result I promised you. In the following result, we show that if a ring admit one absorbing a primary that is not primary, then R has to be quasi-local. So these two concepts are different only if your ring is not, if your ring is quasi-local. If your ring is not quasi-local, that means there is no difference between one absorbing primary and a primary. Okay? Uh, kind of interesting. Well, I don't know what interesting means, but to me it is. So here is the result. Suppose that, yeah, that's what I forgot to tell you. I have to remind you what I mean with the quasi-local ring. I mean the ring has only one maximal ideal. So suppose that R admit one absorbing, that is not a primary ideal, then R has to be quasi-local. That's it. So if your ring is not quasi-local, just forget it. Okay, so the question after that, how if your ring is quasi-local? That's a very good question. How do I construct one absorbing primary that are not primary? That's a very good question. Because I'm telling you that one absorbing primary, they do not need to be primary if the ring is quasi-local. We skip the proof. Because I told you we skip these because if the ring is not yeah, here is what I promised you. The following result provide a method to construct one absorbing primary that are not primary. So you start with the quasi and the result, I mean in the result is the construction. Let R be a quasi-local ring with maximal ideal M. And you choose X in M to be a non-zero prime element, where M is not generated by this prime element. So M is not equal to XR. Then if you multiply M with X, okay, so X, I mean, I don't know why I wrote non-zero prime, because by definition, I think a prime element cannot be zero. Am I right? Yeah, I think it's matter of definition. is not a non-zero and non-unit, the prime element. Then this ideal is one absorbing a primary ideal of R that is not primary. And okay, so look what I did here. I took my quasi-local ring and I selected X in M that is a prime, but not zero, where M is not generated by this element. Then Xm will be one absorbing that is not a primary ideal. Okay, let me go back a little bit to the example I gave you. So the verification of that example I gave you is by this result. Here is the example I gave you. Let's go back. Here is the example I gave you. My R is localizing A at M. Remember my M, the maximal ideal, is generated by xy. Definitely X is a prime element in this ring, right? But the ideal is not generated by X, the maximal ideal of this ring. So how did I form one absorbing primary? I took the maximal ideal, as you see, M localized at M, and I multiply it with X. So by the theorem, you don't have to check for, like multiplication of element and you show. That will be long calculation. But by the theorem, you are convinced now that this ideal here will be one absorbing primary that is not primary. Okay, so what can we do next? Sorry. Sorry, just 1 minute. Ranim, I have a lecture to give. I talk to you later. Sorry, this is my daughter. Uh, okay, all right. So what else I want to tell you? So now we know how to construct uh, 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 one absorbing primary. In fact, here is another way to construct. Look at this result. You take a quasi-local with maximal ideal M and P be a prime ideal of R such that P is a subset of M. Then Pm is one absorbing primary. But this here, it does not tell me it cannot be primary because I can let P to be M. And we know M square is primary. But anyway, maybe this is not a good one to construct one absorbing primary that are not okay. Here is an example, I think, that will work. You take your domain D by Z2 XYZ. Okay, so this example is a product of 2 prime, and the product of the 2 prime are one absorbing primary, but not primary. And you take this H, definitely this H is a maximal ideal of D. And you take a Q XY generated by XY, and you localize R at H. Remember, H is this maximal ideal. So definitely M will be H localized at H. And if you take P to be Q localized at H, this is a prime ideal. Remember, Q generated by XY only. Okay? And if you multiply M with P, so we have Pm is one absorbing, and to show you it is not a primary, here is it. I have xz in Pm, but neither x in the product nor z is in the radical, which is P. Okay? Yeah, here is a very, I mean, I start looking at many interesting properties, like if you have a quasi-local ring with maximal ideal M, and you have A and M is an irreducible element of R. So I have M not equal AR, but AM is a primary ideal of R. Anyway, I think how many minutes left? Am I done? My time?
Sir, 10 minutes.
Ah, okay, maybe I will not use all of them.
Okay, sir.
Yeah, here is another example of what? Of a quasi-local ring where A and M is an irreducible element of R that is not the prime, and M is not equal to AR. M is not equal to AR, but AM is one absorbing that is not primary. Okay? So I start giving example. What about if I select instead of prime element, reducible element? Because we know, I think, every prime is irreducible, but not in an integral domain, of course. And in, yeah, so maybe this is what I was looking at. Yeah, here is a nice result connection. Uh, in fact, if you have I to be one absorbing primary ideal of a ring R, and you take C to be R, take away I, is a non-unit element of R. And then you start looking at all the elements in, I mean, this notation, you see this bracket, I colon C. Here, in fact, I gave the definition. It's the set of all the elements in R where Cx is in I. Of course, we know this is an ideal, but this ideal will be primary. That's a nice result because by now we know how to construct one absorbing primary that are not a primary. But you can construct an ideal on the top of the one absorbing primary that is a primary. How? By this result. Because definitely the ideal I, live inside I colon C by definition. If you choose any x in I, then definitely C x will be in I. So I live inside this ideal. So here is a way to construct, like, you know, you have one absorbing primary, because we know how to construct one absorbing primary that is not primary. And then I can construct an ideal over this ideal that is primary. And this is divided. The first, I think the person who started that, David Dobbs, divided domain. And later on, I generalized this to divided rings. Remind you with the definition of divided, or like, what do we mean with the prime ideal to be divided? Or maybe here in the definition, I gave you the definition of divided in general. So, uh, if you have a prime ideal and you choose x outside the prime ideal, then x has to be a factor of p for every p in the prime ideal p. In another word, in the street language, Divided domain mean if you choose an X outside P, then P has to be a subset or a sub-ideal of the ideal X R. This is how you put it, what we mean with divided domain. Divided domain, again, sorry, divided ring, which is the same definition. Divided ring mean whenever I choose, whenever I have a prime ideal P, and I choose an element X outside P, then the ideal P has to be a subset of X R, the ideal generated by X. Maybe this is simpler than what's written here. Okay, so if you have a divided ring, that's it. Because here is a question you're going to ask me. Is it possible to, uh, and this is a very good question. What is the question? Somebody might ask me, you said if I'm gonna have one absorbing primary that is not the primary, then my ring has to be quasi-local. Are there some examples that are quasi-local, but one absorbing primary is the same as a primary? I tell you yes. Take valuation ring, because valuation rings are divided rings. Take pseudo-valuation rings. Pseudo-valuation rings are divided rings. What this result, and they are, by the way, if you have a divided ring, that's crucial, that means the prime ideals are linearly ordered. That means your ring will have only one maximal ideal. So every divided ring has exactly one maximal ideal. And valuation rings are divided rings. Pseudo-valuation rings are divided rings. Look at this result. Here an example of a quasi-local rings where the two concepts are the same. If R is a divided ring, then a proper ideal is one absorbing primary if and only if I is a primary. Okay? So you can say this is an answer to the question you might have in mind. And as a consequence of this result, you can prove this result. If you have R a divided ring with maximal ideal M, if M is not a principal prime ideal of R, then every non-zero prime ideal is not principal. So if my ring is divided and my maximal ideal is not a principal prime ideal, then every non-zero prime is not principal. Okay? All right. I think I think I told you this result will follow from the divided ring. If you have an evaluation domain, then these two concepts are the same, so there is nothing there. And for a proofer domain, of course, because if you have a proofer domain, that is not, with more than one maximal ideal, then we know that two concepts are the same. Okay, anyway, here are some more. I think that's enough for me. These results you can, in fact, in that theorem, uh, we were not, there are some results, you think they are right, you just don't think about them. We were talking about the ring homomorphism, uh, and this result here, we were not paying attention that when you have a ring homomorphism, does not mean a unit will go to a unit. And remember that our element, the one we select, they have to be non-unit. So it was a careless mistake we made because sometimes you think, these are just routine result. We don't check. So we made a mistake in number one. We have to fix it. And we fixed it in fact, a colleague of mine in Algeria, I thank him, he pointed out the mistake in this one here, number one. And the correction will appear soon in another paper on weakly one absorbing. The correction is there. But I think when you read it, you know what you're going to correct. Here, the mistake we made that we did not pay attention to the definition that A, B, C, they have to be non-unit. We are not selecting element randomly. Okay. And I thank you very much for listening to me. And I thank the organizer for,
Thank you.
you brought a very, very, very outstanding mathematician. And I'm sorry I missed their talk. Thank you.
Thank you so much, Professor Badawi, for such a wonderful talk.